Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 6 on rational numbers and proportional reasoning. Today, we're going to talk about Section 6.3, multiplication, division, and estimations with rational numbers. We will talk about multiplication and division of rational numbers, properties of multiplication and division of rational numbers, estimation of multiplication and division with rational numbers, and then finally, extension of exponents to include negative integers. So one way to model multiplication of rational numbers is with an area model. Here's one way to model 3 times 3/4. So in this case, multiplication is repeated addition because one of the factors is a whole number. So 3 times 3/4 means 3/4 plus 3/4 plus 3/4. Which is 9/4. You can see that one whole consists of 4 parts, and we have a total of 9 parts there. So that's 9/4 or 2 1/4. When both of the factors are fractions, you can represent multiplication as part of an area. So here we have 3/5. If we want to multiply 3/5 by 1/2, we could just cut in half going the other direction. So here is 3/5 across the bottom. Here's 1/2 down the side. And so that cuts this whole into 10 parts. And my product represents 3 of those parts. So 1/2 times 3/5 is 3/10. All right, so the definition of multiplication of rational numbers, if A over B and C over D are any rational numbers, then A over B times C over D is just A times C over B times D. So multiplying is one of the easiest things you can do with 2 fractions. You don't need a common denominator or any of that. You just multiply the numerators and multiply the denominators. All right, here's an example. If 5/6 of the population of a certain city are college graduates and 7/11 of the city's college graduates are female, what fraction of the population of that city is female college graduates? So this is a multiplication problem. It's 7/11 of 5/6. Of tends to translate to multiply. So that gives us 7/11 times 5/6, which is 35/66. The fraction of the population who are female college graduates is 35/66. So a little over half, which would be 33/66, right? All right, identity and inverse properties of multiplication of rational numbers. First of all, just like with whole numbers and integers, the number 1 is the multiplicative identity. It's the unique number such that for every rational number, A over B, 1 times A over B, and A over B times 1 just give you back the same fraction, A over B. And 1 gets to count as the identity element under whole numbers, integers, and rational numbers because it is all 3 of those things. It is a whole number, it is an integer, and it's a rational number. You can write it as 1 over 1, right? All right, what we don't have in either whole numbers or integers is the multiplicative inverse, also known as the reciprocal. For any non-zero rational number, A over B, the multiplicative inverse, or reciprocal, is the unique rational number B over A, such that A over B times B over A, in either order, comes out to be 1. All right, so that's what reciprocals were sort of invented for. You multiply your rational number times its reciprocal, and the answer is 1. This is just showing the distributive property applies to rational numbers. So I'm not going to read this whole thing to you. It's just showing you that if you multiply a rational number by a sum, you can distribute that rational number, whether it's addition happening inside or subtraction. All right, the multiplication property of equality for rational numbers. This is another property that we use to solve equations. So if you have three rational numbers such that the first two of them are equal, you will still have an equation if you multiply both sides of that equation by another rational number. And we usually say that we don't want this rational number e over f to be 0. But the way they've stated it is correct. All right, multiplication properties of inequality, just like with integers. If you start with an inequality and you multiply both sides by a positive rational number, then the inequality will go in the same direction. However, if you multiply both sides of that inequality by a negative rational number, then the inequality will switch direction. Multiplication property of 0, just like with whole numbers and integers, if you multiply any rational number by 0, you get 0. And 0 is a rational number. So that's worth mentioning in this section. All right, here's another example. This is a good one. I like this one. A bicycle is on sale at 3/4 of its original price. If the sale price is $330, what was the original price? Now, a lot of students will look at this and think, oh, 3/4 times 330, okay? But that's not correct, right? Because that's what you would do if $330 was the original price. All right, this time they're not telling me the original price, they're telling me the sale price. So this is really an algebra problem. If you use X to stand for the mystery original price, then the sale price is 3/4 times X. In other words, 3/4 times X is 330. And the way we'll solve that equation for X is by using the multiplication property of equality. We will multiply both sides by the reciprocal, which is 4/3. These two will multiply together to give me 1. That's why this is just X. And then 4/3 times 330 is 440. Notice that answer does make sense. I mean, if the sale price was $330, we know the original price had to be more than that, at least. Okay. So the original price was $440. All right, multiplication with mixed numbers. Basically, you convert your mixed numbers to improper fractions. So if you're trying to do 2.5 times 2.5, you change that 2.5 to 5 halves, and then just multiply as usual. 5 times 5 is 25. 2 times 2 is 4. And of course, 25/4 is 6 1/4. I would probably not recommend doing it this other way, but it is neat to see that it works. And that's using the distributive property. So if you think of 2.5 as 2 plus 1/2, then you can distribute, and that gives you the same answer. All right, division of rational numbers. So this is kind of a difficult concept to wrap your head around if you're hearing it for the first or even second time. Why division of fractions works the way it does. So there are lots of good models for that. For example, if you asked how many 1/2s are in 3 wholes, here's a picture of that. Here are the 3 wholes. And I can actually cut each of those holes in half, and I can count them, 1, 2, 3, 4, 5, 6. So that's an illustration of 3 divided by 1/2 equals 6. How many 1/8s are in 3/4? So we can also draw a picture of that. The shaded green area is 3/4. How many 1/8s can I fit in there? I can fit 6. So 3/4 divided by 1/8 is 6. Here's another one. How many 3/4 are in 7/8? Using a number line model, Here is 7/8, the shaded area. The green shaded area represents 1/4. I'm sorry, 1/3, okay? And then I'm not gonna get another 3/4 out of that. You see this part over here that starts with the little gray area. So notice that this mostly blank area is cut into 1, 2, 3, 4, 5, 6 pieces, and I have one of them shaded. So what this suggests is that 7/8 divided by 3/4 is 1 1/6. So you can see that explained here. All right. So here's the rule for division of rational numbers. Well, really the definition first. So if you have 3 rational numbers such that the second one is not 0, then we say that A over B divided by C over D is equal to E over F if and only if E over F is the unique rational number such that C over D times E over F equals A over B. So it's, again, the mystery missing multiplication number. Think of a simpler, happier time. 8 divided by 2 is defined to be the number that fits 2 times blank equals 8. So we know that number is 4. This is the same idea. It just looks a little scarier because we have to use more letters of the alphabet to represent 3 rational numbers. When 2 fractions with the same denominator are divided, the result can be obtained by dividing the numerator of the first fraction by the numerator of the second. So this is not something that I think about all that much. To divide fractions with different denominators, we rename the fractions so the denominators are equal. Now, we don't always do it that way. It's not a bad way to do it to start with. So A over B divided by C over D, you can write those with a common denominator, and then multiply by the reciprocal. That is really the key to division of fractions. Okay, so in the end, you get AD over BC. Really, we could have skipped this part, right, and just said A over B times D over C, and that would have given me this answer. All right, here's an example. A radio station provides 36 minutes for public service announcements for every 24 hours of broadcasting. So the first question is, what part of the broadcasting day is allotted to public service announcements? So notice that the 2 times are given in different units. We're going to have to make them have the same units in order to do this. And the easiest way to do that is change 24 hours into minutes by multiplying it by 60. So there are 1,440 minutes in a day, which means that 36 over 1,440, which simplifies to 1 over 40. 1/40th of the day is allotted for announcements. How many 3/4 minute public service announcements can be allowed in the 36 minutes? Okay, so this would be an example of 36 divided by 3/4. And of course, dividing by 3/4 is the same thing as multiplying by 4/3. And 36 times 4/3 is 48. So you would be able to do 48 announcements in that 36 minutes. Another example, if we have 35.5 yards of material available to make towels, and each towel requires 3/8 of a yard of material, how many towels can be made? So what we need to do there is find the integer part of the answer to 35.5 divided by 3/8. Notice that we're only interested in the integer part. If this comes out to be a mixed number, well, let's just see what the answer is. 35.5 divided by 3/8, change 35.5 to 71/2. And instead of dividing by 3/8, we'll do times 8/3. that comes out to 94 and 2/3. It wouldn't make sense to say you can make 94 and 2/3 towels, right? You can make 94 towels, and then you'll have a little piece of scrap left over. How much material will be left over? Well, we know it's enough to make 2/3 of a towel, all right? Because the division was by 3/8, the amount of material left over is 2/3 of 3/8. Remember that one towel took 3/8 of a yard, and I had 2/3 of a towel left, so that means I had 1/4 of a yard of material left. 2/3 times 3/8. Another example, a bookstore has a shelf that is 37.5 inches long. Each book that is to be placed on the shelf is 1 1/4 inches thick. How many books can be placed on the shelf? So this would be a great time to pause the video and try this one. Okay, and you never have to wait for me to say that. You know, at any time, pause the video if you want to try any of these first. So we need to find out how many 1 1/4s there are in 37.5. That's a division problem. 37.5 divided by 1 1/4 is 75 halves divided by 5/4. That's what those two mixed numbers are as improper fractions. Dividing by 5/4 is the same thing as multiplying by 4/5. And when you multiply these together, you get 300 over 10, which is 30. So this shelf will hold exactly 30 books with no room left over. All right, that brings us to estimation and mental math with rational numbers. Estimation and mental math strategies that were developed with whole numbers can also be used with rational numbers. So if we wanted to estimate each of these, well, multiplication and then division, all right, estimate each of these answers. How's that? 3 1/4 times 7 8/9. So one way to do that is to say that the answer has to be bigger than 3 times 7, which is 21, and it has to be less than 4 times 8, which is 32. So it's somewhere between 21 and 32. If I was trying to come up with one single estimate, I would probably round 3 1/4 to 3 because it's closer to 3 than to 4. And I would round 7 8/9 to 8. My estimate would be 3 times 8, which is 24. But they just say it's between 21 and 32. And often that's good enough. Now with division, it's a little more complicated. When you're estimating a quotient and you're trying to find an upper and a lower bound, it's not as simple as it is with multiplication. Making the dividend of a division problem larger makes the answer larger, but making the divisor larger makes the quotient smaller. So what you want to do if you're doing a problem like this, let's say I just want to say it's between, you know, one number and another number. The largest that this could be, or let's say an upper bound, would be if I rounded this number up to 25 and rounded this number down to 5. All right, that will give me the biggest possible answer. Actually, that'll be bigger than the exact answer. Okay, round the dividend up and the divisor down. So that would be 25 divided by 5 is 5. So that's an upper bound on the answer. And if I do exactly the opposite, round the dividend down and round the divisor up, that will give me a lower bound. So I will admit that I rigged this problem, all right, so that the upper bound came out to a nice number. 25 divided by 5 is 5. If I round this down to 24, round this up to 6, that's also a nice number. 24 divided by 6 is 4. So this quotient will be somewhere between 4 and 5. All right, that brings us to properties of exponents. I think we've talked about most of these before. We've talked about anything to the power 0 is 1 unless a is 0. 0 to the 0 is undefined. I don't think we've talked about this one before, though. Negative exponent means reciprocal. Okay, so a to the negative m is 1 over a to the m. It's the reciprocal of a to the m. So we'll do some examples with that today. The rest of these I think you've seen before. This is the product rule for exponents, the quotient rule, the power to a power rule, quotient to a power. Okay. When I teach beginning algebra, I usually present this one as a shortcut. It's sort of a special case of letter B. So when you have a fraction to a negative exponent, that's the same thing as the reciprocal to the positive exponent. And then finally, we have the product to a power rule. All right, so using properties of exponents, let's justify each equality or inequality. So all of the statements that are going to come up are true, and they want us to explain them. So for example, why is it that the opposite of x to the power -2 is not the same thing as the opposite of x to the power -2? All right, so let's simplify each of those expressions, and if they come out to different things, then that'll be our justification. Opposite x to the power -2, using the negative exponent rule, is the reciprocal of opposite x squared. And of course, opposite x squared is the same thing as x squared, right? On the other hand, the opposite of x to the -2 means like this, and x to the -2 is the reciprocal of x squared. So the second one comes out to -1 over x squared. The top one comes out to 1 over x squared. So those are not equal. In fact, they are opposites. All right, the next one says the same kind of thing except with a -3 exponent, and it says that they are equal. That's interesting. Okay, so on the one hand, the -3 power of opposite x is the reciprocal of the third power of opposite x. So the reason that these two come out equal is because the third power of opposite x is the same thing as the opposite of x to the third. Okay, so this one comes out to the opposite of 1 over x cubed. And this one works exactly the same way that opposite of x to the -2 did. And it comes out to the same thing. Actually, we could have stopped right here, I guess. All right. Next, why is it that a times b to the -1 is not the same thing as the -1 power of ab? Well, a times b to the -1 is like this. B to the -1 is the reciprocal of b. That expression simplifies to a over b. On the other hand, the -1 power of ab is the reciprocal of ab. So that comes out to 1 over ab, which is clearly not the same thing as a over b. All right, continuing. More examples like this. Why is it that the -1 power of a to the -2, b to the -2 is the same thing as a squared, b squared? Well, that's because of the product to a power rule. The product to a power rule says that you can take an exponent that's out here and attach it to each factor of the product. So a to the -2 and then to the -1. This is the power to a power rule. You multiply these exponents, and that's how you get the 2. And then the same thing with b to the negative 2 to the negative 1. It comes out to b squared. However, that does not work when you replace the multiplication here with addition. And this is a common mistake that algebra students make. They want to say that this is equal to this. I wish it was. That would make life a lot simpler, right? But in fact, the negative 1 power of a to the negative 2 plus b to the negative 2 is the negative 1 power of 1 over a squared plus 1 over b squared. And then adding these fractions, getting common denominators, you would get a squared plus b squared over a squared b squared. And that would be to the negative 1. Clearly, that is not the same thing as a squared plus b squared. Notice what they did. They did away with the negative 1 power by flipping this thing over. What did they call that? Rule G, I think. Yeah, so clearly a squared b squared over a squared plus b squared is not the same thing as a squared plus b squared. All right, next example. Perform the following computations and express your answers without negative exponents. First, we have 16 squared times 8 to the negative 3. So what we're going to do with that is write the 16 and the 8 both as powers of 2. So we'll replace 16 with 2 to the 4th. We'll replace 8 with 2 to the 3rd. 2 to the 4th and then to the power 2 is 2 to the 8th. I multiplied the exponents. 2 to the 3rd and then to the power negative 3 is 2 to the negative 9th. And then we add these exponents to get 2 to the negative 1. So interestingly, 16 squared times 8 to the negative 3 comes out to 1/2, comes out to a fraction. Next, we have 20 squared divided by 2 to the 4th. So let's write the prime factorization of 20. 20 is 2 squared times 5, and we're going to square that. And then we're going to divide by 2 to the 4th. Using properties of exponents, the second power of 2 squared times 5 is 2 to the 4th times 5 squared. And then the 2 to the 4th just cancel each other out. And that leaves us with 5 squared, which is 25. All right, next we have the product of 10 to the negative 1 plus 5 times 10 to the negative 2, plus 3 times 10 to the negative 3. The product of that with 10 to the 3rd, all right? I had an interesting thought when I first saw this problem, and I'll try to remember to share that with you at the end. All right, so what we're going to do is we're just going to distribute this 10 to the 3rd over this sum. And that's going to give us 10 to the negative 1 times 10 to the 3rd plus 5 times 10 to the negative 2 times 10 to the 3rd. You see where we distributed this? So there's 10 to the 3rd, there's 10 to the 3rd, there's 10 to the 3rd, right? Okay. And then the third term is 3 times 10 to the negative 3 times 10 to the 3rd. I think I said that correctly. Okay. So that brings us, using properties of exponents, negative 1 plus 3 is 2. Negative 2 plus 3 is 1. And negative 3 plus 3 is 0. So that comes out to 153 because 10 squared is 100. 10 to the 1st is 10, so this is 50. And then 10 to the 0 is 1, so this is 3. 100 plus 50 plus 3 is 153. So the thought that I had when I first looked at this was, okay, this is 1/10. This is 5 times 1/100th. And this is 3 times 1,000th. So 1/10 plus 5/100 plus 3/1000 is 153 thousandths. This is 0.153 in here. It's the expanded form. And we're multiplying that by 1,000. So that comes out to 153. It's like the decimal point started out here, right here, and then we moved it 1, 2, 3 places to the right. So I thought that was kind of cool. And lastly, we have x to the third, y to the -2. That whole thing raised to the power -4. That's a pretty easy one. Just use the product to a power rule. 3 times -4 is -12. -2 times -4 is 8. And then we don't write negative exponents in our answer. So instead of multiplying by x to the -12, we'll divide by x to the 12th. So the fully simplified final answer is y to the 8th over x to the 12th. And that's going to do it for this section. We'll see you next time.